So far, we have looked at objects that are moving back and forth in a straight line, one-dimensional kinematics. Now that we have seen many examples of solving puzzles in one dimension, we shall expand out to puzzles in 2 dimensions. The techniques of solving 2-dimensional kinematics puzzles are largely identical to those for solving 1-dimensional kinematics. That's because the motion in the x direction in 2D is entirely independent of the motion in the y direction. The variables are largely separate, which means that a 2-dimensional puzzle is more or less just 2 one-dimensional puzzles that have to be solved one after the other. Consider this puzzle. A plane is oriented toward east. Its initial velocity is 40 meters per second, and it is accelerating at 0.5 meters per second squared. However, there is a strong wind pushing it northwards at a constant 15 meters per second. What is its displacement after 30 seconds relative to its starting point? To solve this, we will draw a picture to represent the fact that the plane is flying east but being pushed north. We will take 2 photos, and we will set origin and axes. We'll apply our familiar kinematics variables, but we have to do this in x and y separately. The only thing that is common to both directions is the time. So we draw a table like this. In x, we have displacement, initial and final velocity, and acceleration. And we have corresponding quantities in y. Now, what was the unknown in this question? What is the displacement of the plane? The displacement. But be careful. The plane was moving in x, but the wind was pushing it in y. So both displacements are unknown. What is known? The initial velocity of the plane is 40 I hat meters per second. Its acceleration is 0.5 I hat meters per second. The initial velocity of the wind is 15 j hat meters per second, and the acceleration of the wind is 0. The time is 30 seconds. In the x direction, we are looking for displacement, and we know initial velocity, acceleration, and time. The only toolbox equation that relates all these values is number 2. We substitute the knowns and solve for the displacement. It is 1,425 I hat meters. In the y direction, we are again looking for displacement, and we know initial velocity, acceleration, and time. Again, we use toolbox equation number 2. We substitute the knowns and solve for the displacement. It is 450 j hat meters. So the overall displacement is 1,425 I hat plus 450 j hat meters. In other words, after 30 seconds of flight in the wind, the plane is located 1,425 meters to the east and 450 meters to the north of its original point. Notice that this is a vector in Cartesian notation. We can convert this into polar notation using the equations that we saw in lesson 3. We use the Pythagorean theorem to find the displacement. It is 1,496.36 meters. And we use the arctangent of y over x to find the angle of displacement. It is 17.53 degrees. So, we can equivalently say that after 30 seconds, the plane is located 1,494.36 meters from its starting point at an angle of 17.53 degrees. And although the puzzle didn't ask for it, we could solve for the final velocity in photo 2. In the x direction, the velocity of the plane is 55 I hat meters per second, and in the y direction, it remains 15 j hat meters per second because there was no acceleration. The classic 2D kinematics puzzle is the motion of a projectile. Whenever something is moving horizontally but still falling under the influence of gravity, it is experiencing projectile motion. projectile motion plays a huge role in sports like tennis, football, golf, basketball, and so forth. For our purposes, we will look at a cannonball. Consider this situation. A cannon is at the edge of a 15-meter cliff. It is aimed horizontally. It fires a cannonball at 40 meters per second. Solve for the cannonball's A, time of flight, and B, range. We'll start by drawing a picture. Photo 1 will correspond to where the cannonball was launched and photo 2 to where it lands. We will set the origin as the launch point and the axes such that rightwards is positive x and downwards is positive y. We were asked for the time of flight, so the time is unknown. The second part of the question asks for the range of the cannonball. Range simply means how far away the cannonball lands. It is a synonym for horizontal displacement, the displacement in x. We are told that the vertical distance through which the cannonball falls is positive 15 j hat meters. We also know that it was fired horizontally. That means it had no velocity in the y direction initially, but its velocity in x was 40 meters per second. Finally, the acceleration in y is due to gravity, 9.81 meters per second squared. And unless you are told otherwise, in projectile motion, acceleration in x is always 0. In the y direction, we're looking for time. We know displacement, initial velocity, and acceleration. So we can easily use the second toolbox equation to solve for time. You could use the quadratic formula if you really wanted, but this one is easy enough that you don't have to. You get a time of 1.75 seconds. That's how long it takes for the cannonball to land. If we had tried to solve for the displacement in x first, we would have gotten stuck, because we had only 2 pieces of information in x. But by using the y direction to solve for time first, we now have 3 pieces of information in x. Again, time is always consistent between x and y. It represents the time between the 2 photos. In x, we are looking for the displacement, and we have horizontal velocity, acceleration, and now time. So we can use toolbox equation 2 to solve for the displacement. It is 69.95 I hat meters. We've now solved the puzzle, but while we're at it, we can also find the final velocity in both directions at the landing point. In the y direction, we can use equation 3 to find the final velocity. It is 17.16 j hat meters per second. And in the x direction, we can use equation 1 to find its final velocity. It is 40 I hat meters per second. But here, finding the final velocity in x is pretty trivial. Since the acceleration is 0, the final and initial velocities must be the same. You probably noticed that the calculations we did in the y direction are very similar to the calculations we've already seen for freefall. That's because the cannonball is indeed undergoing freefall in y. It just has an additional independent motion in the x direction tacked on. A variant puzzle is one where the cannon is tilted, usually above the horizontal. In this case, the cannonball will travel upward, reach its peak, and then fall down to the ground. A typical puzzle might read like this. A cannon fires a cannonball at 25 meters per second at an angle of 30 degrees above the horizontal. What is the peak height of the cannonball? As usual, we will start by drawing a picture. We will use 2 photos, one a nanosecond after the cannonball is fired, and one at the instant it reaches its peak. We will set upwards as positive and rightwards as positive. The velocity of the cannonball at the moment of launch, that is, its initial velocity, was 25 meters per second at an angle of 30 degrees. Now, This quantity contains both a size and a direction, so it is a vector. But the direction was expressed in degrees. This vector is in polar notation. You might remember from video 3 that vectors can be expressed in one of two types of notation, polar and Cartesian. When we solve kinematics puzzles, we always have to do them in Cartesian. So we have to translate the initial velocity from polar to Cartesian. Converting to Cartesian means breaking the vector into two components, the x component and the y component. If the angle in polar is standardized with positive x being 0 degrees, then the horizontal component of the initial velocity is given as size times the cosine of angle, r cos theta. That's 25 times the cos of 30 degrees. The cos of 30 degrees is 0.866, and 25 times 0.866 is 21.65 meters per second. The vertical component of initial velocity is r sine theta. That's 25 times the sine of 30. The sine of 30 degrees is 0.5, and 25 times 0.5 is 12.5. So now we have the initial velocity of the cannonball in Cartesian. It is 21.65 I hat plus 12.5 j hat meters per second. Now we can start building our table of knowns. We now know the x component of velocity, 21.65 I hat meters per second, and the y component, 12.5 j hat meters per second. The accelerations are the same as in the last example, 0 in the x direction and negative 9.81 j hat meters per second squared in the y direction. Negative this time because we set upwards as positive. And there's one final piece of information that is implicit. In 1D kinematics, at the peak of motion, the object has to change direction, which means at the peak, the vertical velocity is 0. We now have three pieces of information in the y direction. We can solve for the peak height using toolbox equation 4. It works out to 7.96 j hat meters. That is, the maximum height of the cannonball is 7.96 meters above its initial height. That's what this puzzle was asking for. But while we're at it, we can also solve for the other quantities. We can use toolbox equation 1 to find the time it takes for the cannonball to reach the peak, 1.27 seconds. We can use toolbox equation 2 in the x direction to find out how far it travels horizontally when it reaches the peak, 27.59 I hat meters. And finally, we can use toolbox equation 1 in the x direction to find the horizontal velocity at the peak, 21.65 I hat meters per second. In this video, we introduced some of the common puzzles seen in 2D kinematics. You may run into variants which have slightly different knowns, but they will be solved by using different toolbox equations. In the next video, we will look at puzzles that ask us to solve for other quantities.